In a previous video, we applied the concept of circle inversion to circles inscribed in a honeycomb lattice, like that. And in this video, we're going to look at circles inscribed in a triangular lattice. So let's start with the basic unit, a triangle with an inscribed circle, and that's going to be a unit circle for convenience. Okay, so I have here in this picture a circle positioned with its origin positioned at the 0, 0. The origin is the origin of the circle. The origin of the lattice is the origin of the circle, and the radius is 1. Then I'm going to make the triangle. That's going to be a polygon with 3 sides. I'll call it the radius, the distance to the corner, the sort of the biggest distance from the center is 2, and it's also centered at 0, 0. So this distance is 2, 2, and 2 to the corners, to the vertices of the triangle. And polygons tend to, by default, fill in. So I gave it an opacity of 0, but then I did want to see the polygon. So I gave it an edge form of thick. So there's this thick outline. And then I just added a point at the origin. I'm going to take that away in the later pictures, but I just did want to show the origin in this original. Okay. And then in the triangular lattice, the next one, this arrow, if this arrow is pointing up, and the sort of neighboring arrow, the neighboring triangles are going to be pointing down. And so I had to learn how to do that. So there is so this syntax for a regular polygon was in the curly brackets, the X and Y of the center, the location of the center, and a radius and a number of sides. And they are just choosing in this one where those, is it flat on the bottom? Is it, they're deciding where the vertices go. That's not anything I am controlling here, but they have an extended syntax in which I can control. So now I'm saying that the radius is 2, and I can sort of give it a starting angle. And that was sort of pi on 6. And that gave me my upside down triangle. Okay. So, and I could have done that. I mean, I can, for this one, I didn't have to. It's sort of, it was enough to give it this distance. And I got a triangle of the form I wanted, but I could put an angle here if I wanted. So I could be consistent and always give an angle, but when the syntax without the angle was doing what I wanted half the time. Okay. So now the first thing I want to do in a triangular lattice, so the lattice is just going to be a big collection of triangles. Let me scroll down a little bit and show you. So it's just triangles and triangles and triangles. But first, before I start inverting the circles that are inscribed in the lattice, I want to circle invert the lattice edges themselves. Okay. So there are these sets of parallel lines. There are horizontal lines. There are horizontal lines above and below. There are these, I'll say, negative slope lines to the right and to the left, and there are positive slope lines to the right and to the left. And so the first thing I'm going to invert through the center circle is going to be the lattice edges. Okay. And lines are really sort of circles with infinite radius. And when you invert a circle, you get another circle. And one of the points if the line goes off to infinity, infinity in circle inversion maps to the origin. And so we're going to have a bunch of circles that go through the origin. And so all we really have to find is their sort of center and radii. And so here they were. I'm going sort of 3 parallel lines in each direction. And the 3 is sort of arbitrary here. And so then I am making the horizontal above. Here are their, oops. Here are their origins, and here are their radii. And the lines below have this was 4 plus 6i for every I. So it was 1/4 and then 1/10 and 1/16. The horizontal lines below had radii of 1 plus 2 plus, so this was 2 and 8 and 14, I guess. And then the distance from the origin and the radii are the same. And for the other ones, and all we need to do is give them a direction. So the ones that had a negative slope and were to the right, the angle was pi on 6, cosine for the horizontal, sine for the vertical. Going in the opposite direction, I just added a pi, of course, get me 180 degrees on the other side of the circle. For the positive sloping ones, I had a minus pi on 6. And then for on the opposite side, positive slope, but to the left, I added a pi. And that gave me this. So this big black circle is what I'll call the circle of inversion. And then I colored these lines, the horizontals mapped onto red, the negative slopes to orange, the positive slopes to magenta. And so you'll see here that each sort of interior region has is composed of 3 arcs, and the 3 arcs are different colors. So here's a magenta arc, a red arc, and an orange arc forming sort of this region. And that is the same for all these regions as we go down. All right, so now I want to start inverting the circles, and we're going to go sort of nearest neighbors, next nearest neighbors, next nearest neighbors. Okay, so first I want to draw just the nearest neighbors. And there they are, and I made them green. So here was my original triangle and my circle that I'm going to use as my circle of inversion. And then I have these green ones around it, and they're going to touch the black circle, because as this outer circle becomes an inner circle, this point on the edge that they share will map to itself. So these circles are going to sort of come in. And so here they are down here. Now, compared to the honeycomb, this circle inversion is very sort of sparse, whereas the other one was very dense, more tightly packed. So like here is the previous video, and we see here there were 6 circles, and they so these were the nearest neighbors. The green were the next nearest neighbors. The purple were the next nearest neighbor, and they are fairly tightly packed. So the tight packing of the original lattice gets sort of mapped into a tight packing in the circle inversion lattice. And the triangle it's a much looser. There's a lot more space here than in the honeycomb. Like the honeycomb, there's almost all circle, and there's the hexagon's just a little bit bigger. Whereas in the triangle, there's a lot of space, and that's going to be reflected in the inversion as well. And we can already start to see that here, where you have these, 3 inverted circles and big sort of gaps. All right, now I'm going to add the next nearest neighbor. So this and these triangles keep getting like, here was the original triangle pointing up, its nearest neighbors pointed down, then the next nearest neighbors, these blue, are pointing up again, and it's useful to do that. You sort of one thing you do is to, when you're redrawing the lattice, is it gives you the direction, and for the circle inversion, it's the same direction, just a different distance. So that's sort of why I keep doing this, going back and forth, building up slowly. So this was, the green were the nearest neighbors, the blue the next nearest neighbors, and you sort of go over and down, so you can find that center. This distance from this center to this center is 2, and that angle between the horizontal and that is cosine. So you'll see some, cosine of 30 degrees, which is pi on 6. So you'll see some cosines of pi on 6 floating around. In the positions, in some of the positions, the radii of the inverted circles usually end up to be sort of nice rational fractions, no cosines, no pi's. Okay. So let's see the inversion here. So I have sort of 2 loops, because the number of, there were 3 nearest neighbors, there were 6 next nearest neighbors. And I made this is not this rate, this is the radius of the positions of the circles. So this R here is not the radius of little circles, but the position of the origins of the little circles in the big circle. And so there I say, we've got this cosine of pi on 6 floating around. But here, when I'm making the circle itself, the circle's radius has just a simple fraction, like 1/11. And that seems to be, that usually occurs when you're sort of circle inverting a lattice of inscribed circles the way we are. The radii of the inscribed circles tend to be these sort of nice, simple, rational numbers. And so here then are the next nearest neighbors in blue. And then you sort of compare and you say, the black connects to 3 greens, each green connects to 2 blues, none of the blues touch each other. And so here we have each green is connected to 2 blues, and none of the blues connect to each other, but they are kind of evenly spaced. The blues sort of are evenly spaced, sort of going around, and same in inversion. All right. So I have one more. I have the nearest neighbors, the next nearest neighbors. I'll do the next nearest neighbors, and then I'll be done. I mean, it's not done. You could keep going forever, but it's already getting a little crowded. Not as crowded as, not as packed as the other one, but okay. So first thing I'm doing is I'm drawing the next nearest neighbors, and they are the purple ones. So now there are 3. So there are 2 blues. The green connects to 2 blues, and then there are 2 blues that are going to connect to a circle and not the same blues of the same green circle. Okay, so we'll check that when we do the inversion. And there were 3 of those. So there were 3 original nearest neighbors, 6 next nearest neighbors, and then the next nearest neighbors. I'm drawing down here in purple. In their positions, we've got some cosines hanging about. No, sorry. Yeah, we have the cosines just of their positions, but that distance is a nice 4/15, and then the radius of the circle is a nice 1/15. So the only angles in this one are the sort of three directions to get from the origin, sort of this 90 degrees and these other two angles that are sort of 120 from each of those. Okay. And then last thing is I wanted to put my two pieces together. I wanted to put my lattice edge inversion and my inscribed circle inversion together. And so then that was this last piece. So all sorts of pieces, and that was down here. So this is a fun, colorful picture. We have the circle of inversion, and the sort of the red, orange, magenta, the sort of reddish colors with red in them are the lattice. The blue, green, purple, the ones with blue in them are the inverse of the inscribed circles that were inscribed in the triangle. And we see here that they are inscribed in this inverted lattice. So the inverted circles are inscribed in the inverted lattice, which makes sense. Everything that touched should still touch. Okay, that was circle inversion of circles inscribed in a triangular lattice. Thanks for your attention.